So, PSSN basically built on the very long tradition going back to ADM, 3+1 decomposition into spatial metric and extrinsic curvature. And then in the early 2000s, Pretorius began looking carefully at a very different way of solving Einstein's equations that goes under the name of generalized harmonic. The idea here is to stay four-dimensional and not really go into a 3+1 decomposition, or not as much as in the other formalism. And so we look directly at the four-dimensional Einstein equations. And if you write down, just looking here in vacuum, if you decompose and look into the Ricci tensor in 4D, you get pretty much the same terms we had in 3D, no big surprises here. Sigma G mu plus G rho mu d mu gamma rho plus the other terms that are in the Ricci tensor. The other terms, by the way, are products of two Christoffel symbols contracted in suitable ways. And so if you look at the four-dimensional Einstein equations, we have the same difficulty we had beforehand. We have what looks like a nice wave operator, which would be really nice. And then here again are these other second derivative terms of the metric, which, similarly to the PSSN in 3+1, or ADM, destroy the mathematical properties of the system. One way around this, for the four-dimensional case, how to get around this difficulty was known for a long, long time. And that goes back to the realization that the gammas, this particular combination of gammas, they are again certain contract traces of the full Christoffel symbols. They are actually equal to conditions on the coordinates. If you just take your coordinates x rho and treat them as scalars and compute second derivatives of them, the first derivative gives you a delta function, and the second derivative here turns the delta function into, well, 0 plus the Christoffel term. And so you can get the Christoffel terms out of the coordinates. And one idea to get rid of this nasty term are harmonic coordinates, where this particular combination, let's just give it a name, let's call it box x rho, where box x rho is being set to 0. So if you choose coordinates that are harmonic, then by the choice of gauge, the traces of the Christoffel symbols are 0. And with the trace of the Christoffel symbols being 0, the nasty term has disappeared. Harmonic coordinates go back to the 1920s at least, perhaps even earlier, and were used very extensively in post-Newtonian work. However, harmonic coordinates are ill-suited to evolve black holes with, because the harmonic coordinates develop singularities near the merger of two black holes. And so the same trick of using the coordinate conditions to eliminate the nasty term still works with a right-hand side. And this is where the word generalized harmonic coordinates comes in. So we're choosing coordinates not such that box of x rho is 0, but such that box of x rho is equal to some right-hand side. And that right-hand side can be a function of space and time, and it can also be a function of the current metric, but not of derivatives of the metric. And so if you require a gauge that box of x equals h, then by virtue of here, that means that these traces of the Christoffel symbols are identical to the h function, and so we can substitute the h up into the evolution equation. And so now having the h sitting here, we have first derivatives of h. And if h does not contain derivatives of the metric itself, but only the metric, then the first derivatives of h turn into first derivatives of g, and so we have eliminated the nasty second order derivatives of g. Why did I use the blue pen again? Okay, so we're playing this game here, and then we're substituting gamma rho equals h into our equation up here. If we play this game, changing color, we end up with the wave operator, and we still have this term floating around, which now turns into a terms with rho, and we still have all the other terms floating around that I didn't bother to spell out because they don't matter for the overall structure of the equation. And so now this equation is in principle well posed. It's essentially a set of wave equations for each component of the metric. So we have 10 wave equations. They're coupled to each other with really awful terms on the right-hand side. But those need to be coded, and then life should work well. We can take the 10 wave equations and do a first-order reduction, like the one I described on Monday. Or if you're doing finite differences, you can just take these 10 wave equations and finite difference them in second-order form. If you do either one of these things, you still run into difficulties that things don't work. What fails and what breaks is our gauge condition. Okay. Namely, we have used the fact that, wherever this might be, we have used the fact that h rho minus box of x rho equals 0 to simplify our evolution equations. But in the evolution, we are no longer enforcing the gauge conditions, and so it actually turns out that the gauge condition ends up being violated increasingly strongly during the evolution. If we call this thing capital C for constraint, then in evolutions you find that the C usually grows exponentially. It starts very small because the initial data is really close to being in the precise gauge, but any small numerical errors are exponentially amplified. And this is where another trick comes in that was also developed in the 2000s, first for other evolution systems, and that was also used here. And that trick is to modify the evolution equations yet again. And the precise extra term that happens to work for generalized harmonic takes this form here. So mu minus 1/2 g mu t rho 0. So in this extra term, gamma is just a parameter. This t field is the time vector I was describing yesterday. And C are the constraints. For generalized harmonic, this particular term was first derived and suggested by Gundlach. And it has the following properties. If you're now evolving your equations, and for whatever reason your constraints are already satisfied, the capital C is 0, and this whole green term vanishes. So if you're starting, or if you are constraint satisfying, all is well, we have not modified Einstein's equations. However, if your constraints are not satisfied because of small computer errors, then it turns out this extra term has the property that it exponentially suppresses the constraint violations. So let me write this down. If the C's are 0, we just solve Einstein's equations. All is fine. If the C's are non-zero, then working through perturbations of flat space, the constraints decay exponentially with a decay time that is proportional to this constant gamma here in front. So Gundlach worked this out for perturbations of flat space and could show this exactly. And then Pretorius put it into his generalized harmonic code. And the same type of constraint damping also works and works quite well in curved spacetimes, including black holes. And this constraint damping term was the very last piece of many previous pieces in the puzzle that were missing to get Pretorius' simulations working.
So is that time derivative equation for the constraint, is that one of the Einstein equations? Is that derived from the evolution equations?
It must follow from the Einstein equations because that's all the equations we have. Essentially, you take your constraint, you take the time derivative, and now you re-express derivatives of the metric using the Einstein equations, and that way cut down the order of derivatives you have, and you then identify terms in the equation that you can be replaced by the constraint itself again. Okay. That's all I had in terms of writing things on the blackboard. So for the rest of the, however much longer this is, half an hour, 3/4 of an hour, and full hour, I have a bunch of slides and a bunch of movies with some more recent results. And we can just go through them, we get as far as we get. If there's questions, there's questions. If we have time over at the end, the worst case is I show more movies. Coming back to some of the history again, I was already mentioning over the last few days. This is again the title page of this very first black hole evolution. I got it wrong a few days ago in that the grid size was actually 50 by 150 points, not just 50 by 50 points. And the important thing I've highlighted here is that the evolution time is 1.8 in units of the total mass of the system.
I have the wormhole, isn't it?
Sorry?
It's the wormhole, isn't it?
That's the wormhole. And I just realized, I shouldn't say this, that I actually don't know what's in the paper, I only know the abstract. Then again, 94, 98, Grand Challenge, evolving a single black hole, attracting it through the grid via 6m, the speed of point over the speed of sound. And then fast forward into 2005, 2006, where first Franz had his Harmonic paper, and a few months later, the Brownsville group, Campanelli, Lusto, in Stockholm, and the Goddard Space Flight Center group around John Baker and John Sinclair, both had moving punctures in DSSN working. It was actually a meeting in November 2005 at Goddard, where in the first morning, or in one of the mornings, Franz showed his amazing simulations with the black holes orbiting about each other. And just before lunch, Josef was talking. He was a graduate student back then. He was talking, most of his talk about some obscure topic that I don't remember what it was. And in his last 5 minutes before lunch, he said something like, oh yeah, and by the way, if you make this and this and this little change, then we have black holes that are stately evolving around and emerging. And so it turned into a very long question and answer session. Nobody could believe this. Over lunch, everybody was convinced that putting singularities on your grid and just evolving them and ignoring the singularities could never ever work. And so there was a lot of hectic discussions over lunch. And first talk in the afternoon was one of the Goddard folks, it might even have been John Baker, I don't know who. And he actually spent his whole talk on, yeah, so we are putting our puncture initial data on the grid, we have the singularities, we just evolve the BSSN equations, and it actually seems to work just fine. Here's moving black holes and the convergence tests and the waveforms. And so it was a really memorable meeting with all three results presented at the same time. Franz also had already talked about his results earlier, but both the Brownsville and the Goddard folks, they were really surprised that the other group had essentially had the same results. Here's how Franz's simulation looked like. Center of one of the black holes, about half in orbit or so, or 2/3 of an orbit, and then the black holes have merged. The waveform, you couldn't see anything of the inspiral, essentially chunk radiation followed by merger and clean down. But that was already by far way better than anything else people had been doing beforehand. And the very important thing is that when these cracks gravitational waves have 4 different radii, and time shifts the waves, one actually sees this polar wave propagating out with nearly perfect overlap in the different extraction region. So very, very important paper. And by this time, the evolution time is up to 300. And here's two waveforms being pulled out of the Goddard and the RIT papers. Basically the same story. No in-spiral just yet, but the merger and then the ring down. And even there, just getting the equal mass non-spinning black holes merging, what came already out of these very first simulations is that the merger phase of black holes looks quite simple. You have the two black holes merging into one. The chirp signal goes up until you reach a peak, and then you essentially, without very clear visible nonlinearities, you're just entering the ring down phase. And this very smooth transition is of course the basis that waveform modeling for black holes has been so successful, because there is remarkably little structure in the waveforms. The early days, one of the things that was very quickly realized and then exploited widely were black hole kicks. So if you have an unsymmetric binary black hole, say one black hole more massive than the other one, gravitational wave emission is asymmetric, and during the in-spiral, these asymmetries tend to average out quite well as the system orbits around. However, at the point of merger introduces a certain direction that is preferred, where the peak gravitational waveform is emitted in, and that causes then the black hole being kicked the opposite way. The nice thing about black hole kick simulations is you can do them with very little in-spiral, so 1 or 2 or 3 orbits of in-spiral are good enough to compute what the black hole kicks are. And so early on there were tremendous activities on the black hole kicks. The Jena group had a very good code quite quickly and really nailed down the non-streaming kick systems. So over here, 0.25 symmetric mass ratio is equal mass system. There, because of the symmetries, you have 0 kick. If you go to the very extreme mass ratio case, the little black hole is too little to impart a lot of momentum on the big black hole, so again we'll have 0 kick. So you have a curve that goes up from either end, and the Jena group figured out that the maximum is at around mass ratio, symmetric mass ratio of 0.18 megavolts, with a kick velocity of about 170 kilometers per second. Then, also very quickly, you began putting spins on. And one of the important results are the black hole solar kicks, where you have the 2 black hole spins in the equatorial plane. And depending on the phase of the spins relative to the line connecting the 2 black holes at merger, you got different trajectories of the black holes. For some phases, you got the oscillations during in-spiral and then pretty much low kick later on. But if you had the spins oriented correctly, they were quite large out of plane remnant velocity is possible. And in 2007, Campanelli et al. Argued those could be as large as 3,500 kilometers per second. So that's 1% of the speed of light. Later on, still Rochester, they realized that if you orient the spins slightly differently, not perfectly in plane, but with some component aligned, you could get even higher kicks up to about 5,000 kilometers per second. The first spectral simulations by my collaboration came along fairly quickly thereafter, so everybody else was already doing BSSN, so it was quite simple for them to turn on the few extra little knobs you needed to get the moving puncture simulations going. And that led to this tremendous activities with the kicks around that time, because all the BSSN codes could be turned over into moving puncture codes within a day. We at Cornell and Caltech had already been developing our spectral code, at that point trying to use yet different evolution systems under a variety of names. One of them was called KST, another one was called Einstein-Christoffel, and so forth. But we realized as soon as we saw France's results that generalized harmonic would be ideally suited to be implemented in the spectral code, essentially because of the simplicity of the equations you're solving. That you're really solving a set of scalar wave equations where all the mathematical analysis is very simple, where you can derive boundary conditions rigorously, which is necessary for spectral codes. And so it turned out switching over the spectral code to generalized harmonic was also being possible in very small amounts of time. And so Mark Scheel and Lee Lindblom were the leading workers on that front. And so they switched over spec to generalized harmonic within a month or so. And suddenly, Kerr black holes were totally stable and they were just working. And so what you're seeing here is then a simulation that was started where the in-spiral simulation we had already completed in 2007, about 1 year after Franz et al. But it took us another approximately 1.5 years, especially Mark working on Mark Scheel, getting the merger waveform, the merger part of the system under control. So the first complete spec simulations came in 2009. And because of the high accuracy, this was optimized. This is the convergence plot of this simulation over 15 orbits. At low resolution, the phase error is up at, only goes up to about something like 10 radians, more than one orbit. But you see as you increase resolution that the error goes down remarkably quickly with very little increase in resolution. This is again the beauty of the spectral methods, that when they work, they can work very, very well. But one of the downsides, of course, is the spectral method is also more difficult. That's why this paper here is 2009 and not 2007 methods. So overall, this is a slide I showed quite regularly, is my big shock and awe slide about what's going on in numerical relativity. Just a collection of all the things that were important for the field up to about 2015, because then the slide was full, and then with the primation wave detections, things actually moved so quickly that I stopped updating the slide anymore. We've talked about the ADM formulation, we mentioned Harmonic Lindquist, the punch initial data, Hunt and Kirkman in 1997, the performance and Savage initial data, 1909 and 2003. Just before the big breakthroughs, Bernd Kirkman and Wolfgang Clichy actually managed to get a black hole orbiting around once also with using black holes with punctures, but with a way where you're fixing the punctures, the singularities on your grid, and you're trying to rotate around with your black holes. And that worked barely for one orbit, but then everything fell to pieces. And it turned out that you just let the punctures move over your grid. It was a much more robust way of solving the BSSN equations. What else do we have here? Here is this Rundlach developing the constraint damping that goes into Pretorius' work. And then, of course, 2005, the big things, the 3 different ways of solving Einstein equations. Pretorius' harmonic code, the BSSN punctures, and the SXX spectral code. Here's an overview of the 2 different techniques that are currently used to solve Einstein's equations. And remarkably enough, they are nearly completely orthogonal to each other, and there's almost no overlap. So the puncture initial data from Conrad and Rückmann works very well together with the BSSN equations with moving punctures. And here's the set of equations we had on the blackboard earlier with that type of gauge conditions. And those typically are being run with finite difference codes with adaptive mesh refinement. We talked about finite difference codes with second order in space stencils. Those codes tend to be using 8th order stencils. So instead of 3 grid points, you have 17 grid points. And but you gain a lot higher accuracy that way. The initial data here, if you're thinking about the Brustol diagram for each of the black holes, starts at asymptotically flat asymptotic infinity, spatial infinity, goes to the wormhole and actually covers the entire second universe. And it's over here, this point, where you actually have the puncture in the initial data. The second approach, the conformal sandwich data, we are not going deep into the interior of the black holes. If an initial data slice something like this, we enforce the black holes with boundary conditions and some inner boundary in the domain. I've briefly talked about the conformal sandwich way of solving the equations. Then one uses Generalized harmonic with constraint damping. Certain damped harmonic gauge conditions that are ways of writing down the H functions that go into this formalism. And one of the really nice things that that my collaboration ended up doing is putting a lot of effort into boundary conditions. Because the scalar wave system that comes out of Generalized harmonic has such a simple principal structure, you can actually analyze out all the propagation of information and constraint violations precisely, and you can derive outer boundary conditions that are don't have any reflections, and that also don't have any constraint violations entering your computational domain. So with enough care, one can actually decompose all the fields into all these degrees of freedom are just incoming gauge conditions, these degrees of freedom are incoming physical modes, gravitational waves, those degrees of freedoms are gauge constraint violations. And doing all these decompositions, you can very carefully control outer boundary conditions. And we're doing this with alternate spectrum methods. In contrast, to my knowledge, all the finite difference codes use rather simplistic outer boundary conditions. And I'll come back to that point in a few slides. I'm not aware of any problems because of the quite simplistic boundary conditions, but I'm also not aware of work actually confirming that there is a technique coming from the outer boundary conditions. Praetorius, curiously enough, is the only person who's not falling into straight the left or the right camp here on this blackboard. Praetorius uses the Generalized harmonic system and combines this with finite difference in application format. And he's also doing his own spiel for initial data. Okay, I thought I could give a few slides of overview and more insights into the spectral Einstein code. I'm picking the spectral Einstein code because I'm one of the authors there, not because I want to talk badly about the BSSN codes. It's just I have more plots available for spec than for any other code. To give you some sense of scale, big relativity codes are big. So spec is about 600,000 lines of code. And quite a long list of people who have contributed to the code on more or less intensely over the last 15 years. Including quite a few people here in the room. Catherine is in the background, Aaron Zimmerman is in the background. That's how about it? I have already explained this yesterday, that we decompose into basis functions. The domain decomposition is also the means to parallelize back, in that each of the many subdomains is being put on a different processor. And that way we can bounce back in about 50 or 60 cores or so. Which, when we begin writing spec 15 years ago, we thought this is plenty of parallelization, we don't need to worry about more. In the meantime, this has become one of the big limitations, that we can't parallelize spec better, and that therefore the simulations take longer than we could wish. We've talked about the evolution equations over in the blackboard, so I don't need to go to that slide again. But we've also talked about the way you do boundary conditions. You rewrite the system of equations in first order form, with complicated matrices A floating around the spatial derivatives. And you then do an eigenvector decomposition of that matrix A multiplied with the propagation direction. And the eigenvalues tell you how many boundary conditions you need and of what fields you need the boundary conditions. Laconic excision is a concept that's remarkably easy to explain. That as you go inside your black hole, the light cones are turning over. And so if you have an artificial boundary just inside the black hole horizon, the light cone is on one side. You can put the boundary there, but because all the information flows into the black hole, you actually don't need boundary conditions. And because of that, you can avoid having to deal with the singularity in the middle of the black hole, and you can happily evolve at the outside region where the solutions are smooth and well behaved without having to worry about all the nastinesses that's happening in the middle of the black holes. Yeah, fat chance, nice little idea, but if you actually want to make it work in practice, it is remarkably difficult. One thing you run into is that you cannot just keep your excision boundaries constant, and whenever the black hole has moved far enough, you discontinuously change them. Because on the horizon, the light cones are tangent to the horizon, and so slightly inside, the direction of the light cone will be inside the horizon, so this works well. But if the horizon is moving relative to the excision boundary, you can have the situation indicated here, that the horizon is completely on one side of that the light cone is on one side of the horizon, as it must be, but that the excision boundary is intersecting the light cone. And if that's the case, one still must put boundary conditions and such an inner boundary. But one doesn't know what boundary conditions to put there, so that's difficult. In principle, whatever boundary conditions you put here, the information cannot propagate out of the black hole, so in principle it should be fine. But numerics never works as simply, especially if you do spectral methods that couple everything within a computational domain. This doesn't really work out. So what we ended up doing is, we ended up coding continuous coordinate transformations that make the excision boundary continuously track the horizon location. And it also deforms along with the horizons via merger, such that the excision boundary can remain very close to the horizon all along. So this is a typical grid of a spec simulation just before merger, where you're seeing here a lot of elements, many more than I had in my simpler cases early on. You're also seeing how deformed the black holes become, and that all these deformations have to be tracked quite accurately. That's another point, by the way, where the transharmonic evolution equation helps a lot. GH has all characteristic speeds less than or equal to the speed of light. And so you actually have all information propagation inside or on the light cone, and that's essential to making black hole excision work. BSSN with standard parameters, there are modes that move faster than gauge modes that move faster than the speed of light. They don't seem to mess up the simulations, but they would not work well with black hole excision. Outer boundary conditions. As already pointed out, one can derive very fancy boundary conditions to preserve constraints and to avoid reflection of the outgoing gravitational waves back in. Lee Lindblom has been the primary person working out all this theory. And the important thing to note here is that the spec simulations, and by now also quite a few of the BSSN analytical simulations, are long enough that the outer boundary is causally connected to the strong field regime. So at that point, one actually needs to worry carefully about whether the outer boundary could introduce phase errors and other difficulties back into the computational domain. In fact, we actually tested this quite a few years ago when we were working at simulations of mass ratio 2:6. And so we've done simulations with 3 different locations of the outer boundaries. The nice thing is when you have this type of domain decomposition, you can move the outer boundary further away by attaching more of these spherical shells. They have high radial resolution because you need to resolve the outgoing waves. But all these shells have the same low angular resolution because the gravitational waves are dominated by L equal 2, and even L equal 8 is already a lot smaller than the amplitude than the L equal 2 modes. So we can move the outer boundary further away with a cost that is linear in the location of the outer boundary, and not cubic as it would be for finite difference Cartesian codes. So doing that, we actually have run simulations with totally identical inequal decomposition and only attaching more and more spherical shells to the outer radii. And that way we have run these unequal mass simulations with 3 different outer grid radii. What's shown here is the difference in the gravitational wave phasing between the different simulations. The dashed lines that are going down a little bit, those are the phasing differences between outer boundary at approximately 400 M and approximately 600 M. And you see those go down to about 0.01 radians or so towards the merger. The different curves here are offset from each other for ease of plotting. Whereas if we take the difference between the normal outer boundary radius of about 600 and one that is about 900, you get the solid curves that are even flatter than the looking at the small outer boundary radius. So we can actually quantify the impact of the outer boundary radius on the phasing of the waveforms. If somebody has done something similar for BSSN simulations, I would love to know that. But because I'm still not aware of any such test ever being done with the BSSN codes. And then eventually you can put everything together and things work and you can make nice movies. This is one done with spec by the movie was done by myself during my sabbatical. This is the system consistent with the first gravitational wave detection. So you see the 2 black holes, and below you see a cut in the instantaneous equatorial plane of the binary, where this lower plane is the height represents the spatial curvature, and the color coding represents the lapse function, the rate of flow of time. And eventually the two black holes are going to collide from a bigger black hole and then ring down. Also shown in the plane, in purple at somewhat larger distances, are the outgoing gravitational waves heavily traveling off and billion years later hitting the LIGO detectors.
Sorry, what were the color and the depression again? What were they?
So the depth is, roughly speaking, minus the trace of the spatial Ricci tensor. There is a certain transformation being put in to make everything look more pleasant. And the color is the lapse function. And the arrows are the shift vector. And the black holes are also color-coded. They have their northern hemisphere color-coded in red and yellow. So you can actually see how the black holes are precessing because of the generic spin orientations that are put on this particular simulation. Yeah, one important thing that came also out of the first few years of black hole simulations was this question of how good post-Newtonian actually is and how much extra work it has to do to model the inspired of the gravitational waves. So this is one thing you could do even for our very first Tipton orbit simulation before we even had the merger. So what's going on here is the simulation is about 4,000 n long until the code crashed. And it crashed about 2 Parisian wave cycles before merger, and the whole thing was about 36 cycles long, as indicated in the top panel. And the game we are playing here, that at this point, about a third into the simulation, we were aligning phases, frequencies, and so forth in the numerical simulation with a bunch of different post-Newtonian approximates, Taylor T1 through Taylor T4. And for this particular case, if you have 2 PN order, everything must agree by construction where we have aligned things. But as you go later, everything goes out of phase. If you go earlier, things also go out of phase. And so that's the indication that second post-Newtonian order isn't good enough for non-spinning black holes at this particular point in the sky. But we can now go up and increase the post-Newtonian order, and things are actually converging very, very nicely. And that's important in a few different ways. One of the very important aspects from the numerical side is the very good agreement now early on as a validation that the numerical code actually works as expected. And also from the post-Newtonian side, to get a sense of how well post-Newtonian works, and to clear up a confusion that was floating around for a year or so in the community, that post-Newtonian theory actually works all the way to the end. For reasons unclear to me, it turned out that the early post-Newtonian comparisons were all done with Taylor T4. One particular way of writing post-Newtonian theory, if you look at the inspiral, nearly perfect agreement over here, here's the last 2 cycles blown up, still nearly perfect agreement all the way 2 cycles before merger. So, seemed like post-Newtonian is really, really great, until you look at some other post-Newtonian approximant, which picks up quite a bit more defacing. And it turned out that Taylor T4 for equal mass non-spinning, by pure coincidence, happened to match the reality much, much better than anybody had any expectation for it to work. If you change the approximate and equal mass non-spinning, like going to Taylor T3 or T1, it doesn't work. If you keep Taylor T4 but change the mass ratio, it also doesn't work as well anymore. It was a pure coincidence that Taylor T4, at the simple case that everybody was comparing first, worked so well. Also, over the years, there have been already quite a few numerical relativity code comparisons. And that's very important because these codes are so complicated, all of them. I've showed you a few details about spec. It's really complicated. The BSSN codes are slightly less complicated, but still they have the moving punctures that early on people weren't quite comfortable with. And since these waveforms are going to be used for LIGO, gravitational wave analysis, and LIGO is a very expensive and flagship experiment, one really needs to be as sure as one can that the waveforms computed are actually correct. And the really nice thing is that we have this numerical relativity, these two totally different ways of solving Einstein's equations, different initial data, different evolution equations, different numerical methods. And so there's a lot of redundancy in the system, and comparisons like here, where all the different codes actually agree with each other within the line thickness, are very meaningful tests that the community really understands how the codes work and what the answer is. That was the first such comparison in 2009. It was called Samurai, because just before there was another community project called Ninja. And if you have ninjas, then Mark Hannon wanted to have samurais. That's a comparison for the equal mass non-spinning binary black hole case. Let's plot it up here, 5 different codes. Down here are the phase differences between the different codes. Spec is serving as reference as 0, and so you see that phase differences relative to spec. Some codes are either 0.1 radians, others are either 1 radian, but everything agreed remarkably well. Here's a newer comparison, spec versus RIT. This is for a system that was actually then used for the analysis of the first gravitational wave discovery. And as before, the two different numerical relativity simulations are within the line thickness of each other. Down here is quantified the difference between RIT and spec in terms of mismatches. And so the mismatch is always below 10 to the minus 3 or reaching 10 to the minus 5. Whereas the waveform models that were used around that time actually had mismatches of approaching 0.5%. So it wasn't the numerics that was the limiting factor, it was the waveform models. And by the way, this very waveform that's plotted up here, that's actually plotted twice, is the one that then made it into the one of the flagship LIGO figures for the gravitational wave discovery. And so while the numerical relativity codes aren't reviewed, at least we are, by the LBC, at least we have made sure that independent codes gave the same answer. Okay, so over the years also, one important thing is to explore all the parameter space for the binary black holes. The top 3 waveforms from 506 I already showed you earlier, and very quickly the Goddard group added quite a bit more cycles to it. And then over the years, things became bigger and bigger. So in 2009, the first Ninja project collected all waveforms that were available at that time worldwide. It's this panel here with about 20 or so waveforms. That's all that was around in 2009. The longest one was the one specs waveform in the system up here, and then the rest of them is BAM and CKT was, I think, the AEI code. There's also some from Johanna Champagne and from Gina on here. But as you see back then, the number of waveforms and the length of them was still quite short compared to today. Top right was then the first big waveform catalog that my collaboration put out, 170 waveforms, and was still just barely was able to plot them all, but in order to actually see something, we had to zoom in. Because the one thing spec is really good is making longer simulations, and so these were typically 20 to 30 orbits long. By now, there's thousands of simulations worldwide. BAM, Cardiff, Palomar, quite a few students here have been quite active working, computing waveforms that are used in mostly the phenom waveform models. Georgia Tech has been simulating many systems, usually shorter simulations focusing on merger and ring down characteristics of the black holes. RIT has the, I would guess, monopoly these days on computing remnant quantities, masses and spins and kicks more accurately than others, and deriving ever more complicated remnant formulae that give the final properties in terms of the initial data, initial conditions. And SXX again is putting a lot of work into waveform modeling, so long simulations. They're used to map and develop the SUB&R waveform models. Also, a lot of the SXX waveforms are used for the phenom waveform models, and as I mentioned, I'll soon get some of the slides in the near future. So as you've heard last week, and perhaps more later this week, there's a lot of effort going into taking these numerical waveform models and turning them into complete instantly merger ring-down waveforms that can be easily evaluated quickly, and that are then in use for the light data analysis. There's two big families of such models around. One goes under the name effective from body models. The other goes under the name of phenomenological models. And all of these have a large number of free parameters somewhere built in. And all of these are fitted against numerical simulations of the last 10 orbits or so, merge and ring downs of the black holes. Everybody's quiet, no questions?
Only one thing. The poor angular resolution of that you mentioned, it affects the accuracy of the higher modes of the simulation. So if you will need to extract the L3, L4 modes of the waveform, you can accurately.
We've looked at that early on, and we now typically use L equals 16 or thereabouts in the outer spherical shells. So still significantly more than the L equals 8 modes that we are commonly extracting and reporting. But I'm not aware that we have done a recent test whether this outer angular resolution impacts the solution. I don't think it does, but it would be worthwhile to run another test on it.
What's the current status on comparing directly to Poisson-Shannon approximations for the spiral? I know that there's the very long simulation from Bela and Jonathan, but it had large errors, numerical errors. And you also had non-doing these kinds of studies at some point, right?
So we did studies. Let's see whether I actually kept this slide here or not. Um, I might have it. I hope I have it in this one. Short answer is not much has happened.
That was my impression, but I'm sure.
I don't find the plot. So this post-Newtonian comparison here looks impressively good for a few different reasons. One reason is that the equal mass systems spiral in so quickly that you don't really have many cycles. And as you increase mass ratio, the system spends more and more cycles at high frequencies, at high velocities. So post-Newtonian errors tend to be growing quite quickly with the mass ratio if you go to unequal mass systems. So while here for equal mass I would think of sandy dandy, there are some preliminary analysis how this works for unequal masses, and even for mass ratio 6, the conclusion was you don't need 10 orbits, you need 100 orbits for numerical relativity. And people got very depressed. And if you put on spins, again the match with post-Newtonian became worse because the spin post-Newtonian terms weren't apparently known as well as they should be for getting the high precision. And so this is in some sense the best possible outcome for post-Newtonian theory. But I don't remember any concrete further phasing comparisons. Sergei did some for his precessing ones, where the conclusion was precession doesn't really make post-Newtonian better or worse. The phasing is bad no matter if you have precession or not.
What mass ratios did you go up to?
2 or 3. Yeah, and this waveform modeling and fitting, of course, keeps on improving. Here's a result from a new big set of aligned spin simulations that we published in 2015. And I think that became publicly available late 2016 or so. And they were exploring larger spin magnitudes than before. And so, as soon as you plugged in the larger spin magnitudes in the waveform models, like here SMP and OP2, it wasn't fitted against large spin magnitudes, so they ended up getting bigger errors than anticipated, whereas most of it is bound to be 1%, 0.1% mismatch. And then having the new data set and having identified when parameter space the model is deficient, our collaborators around Alessandro Bonanno and her group went in and improved the B model, and the E4 model now is better by about a factor of 20 or so in terms of mismatches than the B2 model. And the same sequence of steps also happens for the phenom models, that there is this long list of letters, phenom A, B, C, D, then they jump to X. With each letter further down the alphabet, the models became significantly better than before. Because one had more data to work with, and because one had more experience with what precise features in the waveform models are important to improve the overlaps in between. I mentioned surrogate models very briefly early on, so I'd like this to do a little bit of plug on it. It turns out the amount of structure in binary black hole waveforms is small enough that you can actually just take of the order of about 1,000 or so simulations, particularly 744. And with enough applied math tricks, you can use these 744 simulations and without ever doing an analytic intermediate model, from it construct what is called a surrogate model that behaves remarkably well. So in this particular case, the blue one are the errors in the surrogate model, to be clear, mismatches in E10 minus 4 and 10 minus 3. Whereas comparing to PE2 of the processing error models and the processing UV models, those were having mismatches more like a few percent. And this particular, most of this disagreement came about because these two waveform models don't yet have higher order modes. Whereas the surrogate model not only included precession with all 3 degrees of freedom of spin, it also includes higher order modes up to level 4. And so the combination of not having to fit plus having the higher order modes already built in automatically through the applied math techniques in the surrogate modeling made this model actually quite a bit better than the Eligible 2 based processing waveform models from last year. By now, everybody is working on processing higher order mode models, and it will be interesting to see where then the phenomenon the EOB models land if you have processing models with higher order modes, which would push them to the left. The question is just
how many simulations would you need to extend to higher mass ratio the surrogate model?
Thank you for pointing this out. Surrogate models work well within the range of parameters that you can cover. And so, for this particular one that looks so nice, the mass ratio only goes up to 1/2, and the spin magnitude is only up to 0.8. The number of simulations is quite comparable if you go up to mass ratio 4, 6, 8. It's same order of magnitude, a few hundred to 1,000. It's just that the simulations become more difficult as the mass ratio becomes larger. And so the next model is one that goes up to mass ratio 4 that should be published in the not too distant future. A few records in all this waveform modeling. I already mentioned earlier that in terms of spin, the biggest spin simulated right now are 0.998. The difficulty with these high spins is that for black hole excision to work, you need to have the excision boundary between R plus and R minus, the outer and the inner horizon of the Kerr black hole. Because inside R minus, inside the inner horizon, the light cones tip over again. However, as the spin goes up, the distance between R plus and R minus becomes increasingly small. And so all the horizon control has to be ever more explicit. Mass ratio, the band folks, Sasha Buser and company are currently the leaders with the mass ratio 18 simulation that is long enough to be useful for waveform modeling. And in sheer length, there's this 350 orbit simulation that Bela Silaci was running about 2 or 3 years ago at Caltech, mass ratio 7 and without spins. That's the one Aaron was referring to earlier on. It's really long, and it turned out, given that length, the outer boundary radius did matter a lot and did impact the solution. However, by the time we noticed this, the solution had been running all the way over here. And this was about 3/4 of a year, and so it was not easy, not an option just to rerun this with the outer boundary further. Yeah, and the right one, the yellow thing at the right, this is one of the shorter simulations that I showed earlier, where we had tested the outer boundary impacts. So there was a difference between running 15 orbits and running 150 orbits. Also, we've been beginning to explore generic systems. Eccentric processing. Aaron has been quite big in running these systems. I especially like this particular plot here that shows the 40 orbits or so of a mass ratio 7 system. And it very much looks like Steve Dresco's movie of a small body going in on generic geodesics around a great black hole. This dot, by the way, is the second black hole. It's not the bullet point for the text on the right hand side. Okay, that's all I had. And to close this out, I'm showing a movie probably many of you have already seen before. And I wanted to start this up with a little bit more about lensing. So this is the image of the galaxy that is used in the background of the famous lensing movie. This one here. Except that I have highlighted 3 stars. And this is the same angle of view. And so you see how the stars are moving around. And of course they're getting shifted out since the waves need to go around black holes in the middle. So if you look, for instance, at this green point here, this is moved to the right because the waves need to go around your 2 black holes. What I found quite neat is if you stare at this image long enough, you find more images. So here's the same star again. This time the light goes around the opposite way around the 2 black holes. And you can also go through the middle. And so here's the same star again. And at that point, I don't have enough resolution to actually see this anymore, but I imagine that if you look at between the black hole and the projection of the other black hole, you could actually find a trajectory that first goes behind the first black hole, comes before the second black hole, and that should end up as another image over here. So you can play this game as long as the resolution of your ray tracing allows. And then if you turn on this whole thing, as done by Andy Borman and Will Throw, mostly at Cornell, you get this beautiful movie that made the rounds around 1509-14 announcement. And the first movie was mine, the one with the play. With this movie, I have nothing to do except that I like it a lot and benefit from being in the collaboration to be able to show it as well. That's all I had, so thank you very much for your attention.